Hello and welcome back. In our today's lesson, we are going to apply the equation we derived in our previous lesson, that is the CLAPEYRON'S equation of three moment, or in other words what we call the three moment equation. And we are going to apply it today to plot the bending moment as well as the shear force diagram for the beam shown in the figure below. Now, the beam shown in the figure below is a continuous beam and it is being supported by three supports. We have support A, support B, as well as support C. So, ladies and gentlemen, join me so as we go step by step to solve the problem that we have here. If you are here and you are yet to subscribe, please consider subscribing. And don't forget to hit the notification bell as well. Now, the first thing we are going to do, we are going to consider the span AB. Therefore, consider span AB. Good. So, the very first thing we are going to begin with, we are going to begin with calculating the bending moment at the points of actions of these 2 point loads. Therefore, we are going to begin with calculating the bending moment at point D. Therefore, if we consider span AB, you will find that the beam AB is simply supported, and therefore we are going to have this. The beam AB is simply supported, and therefore bending moment at D. Since the beam AB is a simply supported beam, the bending moment at D is going to be equal to W1 A1 B1 over L1, whereby L1 is the span A to B, that is 3.6 meters. A to D, that's going to be A1. B to B, that is going to be B1. Therefore, we are going to have this. W1 is 2 kilonewtons, that is the point load at D. Therefore, this is going to be 2 kilonewtons multiplied by A1, that is the distance from A to D, 1.8 meters, multiplied by another 1.8 meters, the span between D and B, 1.8 meters, and then we divide by L1, that is 3.6 meters. And this is going to give us a bending moment of 1.8 kilonewton meter. Therefore, the bending moment at D is 1.8 kilonewton meters. Now, after getting the bending moment at D, we are going to calculate the bending moment at E, and in this case, we are going to consider the span BC. Consider the span B to C. Now, likewise, the beam BC is also simply supported, and therefore the bending moment at point E, where we have a point load of 4 kilonewtons, will be given by W2 A2 B2 all over L2, whereby A2 is the distance between D and E, B2 is the distance between E and C, and L2 is the span between B and C. And therefore, this is going to give us W2, which is 4 kilonewtons. Therefore, you are going to have 4 multiplied by A2, that is 0.6 meters, multiplied by B2, 1.8 meters, all over 2.4 meters, that is L2. And therefore, the bending moment at E will also be equal to 1.8 kilonewtons. 1.8 kilonewtons. Good. Then from there, After getting the bending moment at D as well as the bending moment at E, we are going to plot the bending moment diagram due to vertical loads. And we are going to have this. We have the line of origin here, the line of origin. Then 1.8 newtons, let's assume it is at that point, that is the point D. Therefore, we are going to join that point to the 1.8 kilonewton bending moment, and then we join it at that point. Therefore, this maximum or this apex of this triangle is 1.8 kilonewton meter. 1.8 kilonewton meter. That is this one, bending moment at D. Bending moment at E again, 1.8 kilonewton meter at this point. Therefore, we are going to join this one there, then drop it up to that point. So this is also a bending moment of 1.8 kilonewton meter. Then the next thing we are going to determine is the area of this bending moment diagram between span A and B, as well as between span B and C. Therefore, we go to area of bending moment diagram. Area of bending moment diagram for span AB. For span AB. And that area, the area of this triangle, that is A1, will be given by a half multiplied by the base. The base A to B is 3.6 meters multiplied by the height, which is 1.8 units, 1.8 units. Therefore, this is going to give us 3.24 square meters. 3.24 square meters. Then we determine the distance of center of gravity of this, that is the distance of center of gravity of this triangle here, of the triangle in span AB from A, and that is bar x1. That's going to be bar x1. Therefore, bar x1 is going to be the distance from the center of gravity of this triangular section all the way to A. Therefore, bar x1. That's what we are going to determine next. And bar x1 will be given by L1 plus A1 divided by 3. So that is the formula we use. And this is going to be equal to L1 is 3.6 meters plus A1 is 1.8 meters, and then we divide this by 3. And when we do that, we are going to get 1.8 meters. Therefore, this is going to give us 1.8 meters. 1.8 meters. Therefore, it means that the distance from the center of gravity of this triangle all the way to A is 1.8 meters. Therefore, after getting that, the next one will be area of the B.M.D. Area of the bending moment diagram for span BC. For the span B to C. Area of bending moment diagram for the span BC. Now, it is also a triangle, and therefore A2 is going to be given by a half multiplied by the base of this triangle, that is the distance from B to C, which is 2.4 meters, multiplied by the height of this triangle, which is 1.8 units. So multiplied by 1.8, and therefore A2 will give us 2.16 meters, 2.16 square meters. Therefore, that is the value of the area A2. Then the distance of center of gravity, distance of center of gravity of the triangle, in the span B to C, in the span B to C, from the end C, from the end C. Therefore, we need the distance of the center of gravity of this triangle from C, and that is going to be bar x2, bar x2. We also need it. Now, to get bar x2, we are going to use this formula, L2 plus B2 all over 3. So this is going to be equal to L2 2.4 meters plus B2 is 1.8 meters. Then we divide this by 3, and that's going to give us 1.4 meters, 1.4 meters. So that is the value of bar x2. From there we applying the 3-moment equation. Applying the 3-moment equation, we are going to get the following. We get now the 3-moment equation states that MAL1 plus 2MB plus 2MB into L1 plus L2 plus MCL2 is going to give you 6A1 bar x1 divided by L1 plus 6A2 bar x2 divided by L2. That is how it states. Now, the bending moment at the end supports, that is support A and support C, are going to be 0. And therefore, we are going to say this. MA is equal to MC, which is equal to 0. It is equal to 0. Therefore, we are going to remain with the calculation of the bending moment at B. Good. So, we continue with the application of the 3-moment equation. Now, we are going to have the whole of this is going to be 0, so we are going to remain with 2MB into L1. L1 is 3.6 meters plus L2 2.4 meters. So is equals to 6 multiplied by A1, which is 3.24 meters, multiplied by bar x1, which is 1.8 meters, all over L1, which is 3.6 meters, plus 6 multiplied by A2, which is 2.16 square meters, 2.16 square meters, multiplied by bar x2, which is 1.4 meters, 1.4 meters. We divide this by L2, which is 2.4 meters, 2.4 meters. Very good. So this is going to give us a 12 equal to, when we multiply this, it is going to give us 9.72. So is equals to 9.72 plus, when we solve the other part, we are going to have 7.56. Therefore, MB is going to be equal to, when we add 9.72 plus 7.56, that is going to give us a 17.28. Then we divide by 12, and therefore the bending moment at B is going to give us 1.44 kilonewton meter. Now the bending moment at B is going to be negative 1.44 kilonewton meter. The reason being, this beam, when it bends, it is going to sag between A and B, but at B it is going to hog. We are going to have a hogging, the beam is going to hog there, and therefore when that is, hogging is usually negative and sagging is usually positive, and therefore the bending moment at B is going to be negative. So we are going to plot that bending moment at support B, which we have as 1.44. Therefore, if I approximate 1.44 to be that point, we are going to have this. And then we join that point to this corner at C. Therefore, this is 1.44 kilonewton meter. Therefore, as we have said, the bending moment at B will be negative, but this one is going to be positive because it is a sagging moment, and this one is also going to be positive. So from there we can do what we call a shading the outline of the positive part of the beam, shading the outline of the negative part of the beam, and as well as this part we shade it off so that they become clearer and clearer and more visible. So ladies and gentlemen, that is how we plot the bending moment diagram for a continuous beam. So the next thing will be plotting the shear force diagram, and for us to plot the shear force diagrams, first of all we are going to calculate the values of the reactions at the supports, reaction at A, at B, as well as at C. Therefore, we go to reactions, calculations, and we are going to begin with the span BC. Therefore, consider the span BC. Consider the span BC. In the span BC, we are going to take moments, about B. Taking moments about B, we are going to get what? Good. So this is going to be RC multiplied by the distance from C to B, which is 2.4 meters. Remember, that is an anti-clockwise moment. So we are going to have this RC multiplied by the distance from C to B, which is 2.4 meters, plus the bending moment at B, which is also an anti-clockwise moment of 1.44 kilonewtons, is equal to this clockwise moment of 4 times the distance from E to B, which is 0.6. Therefore, is equals to 4 times 0.6. Good. So this is going to be RC times 2.4 being equal to 4 times 6, which is 2.4, minus 1.44, RC is going to be 2.4 minus 1.44, that is 0.96. So that is going to be equal to 0.96, and then we divide by this 2.4. So that is going to give us a reaction of 0.4 kilonewtons. Therefore, the reaction at C is going to be 0.4 kilonewtons. From there, we go to the span AB. Good. So we are going to say this: consider the span A to B. Consider span AB, taking moments about B as well. Taking moments about B, we are going to get the following. Therefore, we are going to have this anti-clockwise moment. This clockwise moment, I mean, a clockwise moment of RA times the distance from A to B, which is 3.6 meters. So that's going to be RA multiplied by, therefore, RA multiplied by 3.6 meters plus another clockwise moment, that is the moment at B of 1.44 kilonewtons. 1.44 kilonewtons is equal to 2 kilonewtons times the distance from D to B, since we are taking moments about B. So that is going to be 2 multiplied by 1.8 meters. So this is going to be RA times 3.6 being equal to 2 times 1.8, definitely that is 3.6. 3.6. Take 1.44 this side of the equal sign, that is going to be minus 1.44. Therefore, RA is going to be equal to 3.6 minus 1.44, that is going to be 2.16. So is equals 2.16. We divide that by 3.6. And that is going to give us a reaction of 0.6 kilonewtons. Therefore, the reaction at A is 0.6 kilonewtons. From there, we need the reaction at B, and this one we are going to use this. The sum of all the upward forces must be equal to the sum of all the downward acting forces, and therefore we are going to have this reaction at A plus reaction at B plus the reaction at C is going to be equal to the downward acting forces. We have 2 kilonewtons as well as 4 kilonewtons. Therefore, is equals 2 plus 4. RA is 0.6 kilonewtons plus RB, which we are calculating, plus RC, which is 0.4 kilonewtons, is equals to 2 plus 4, which is 6 kilonewtons. Therefore, RB will be given by 6 minus 0.6 plus 0.4, that is 1. So 6 minus 1, which is 5 kilonewtons. And therefore, the reaction at B is nothing else but 5 kilonewtons. Good. After getting the value of the reactions, the next thing is going to be calculation of the shear forces. Therefore, we go to shear force SF calculations. Shear force calculations. Now, in this case, we are going to have this: the shear force between C and E. Shear force between C and E, that is going to be 0.4 kilonewtons. 0.4 kilonewtons. That is the shear force between C and E. 0.4 kilonewtons. From there, you go to shear force between E and B. E and B. That is going to be this 0.4 kilonewtons minus the downward acting force of 4 kilonewtons, because it is acting in the opposite direction of the reaction at C. So that's going to be 0.4 minus 4, which in this case is going to be negative 3.6 kilonewtons. Then the next shear force will be the shear force between B and D. Therefore, we go to shear force between B and D, which is going to be this negative 3.6 kilonewtons plus 5. That is the reaction at B. So we add 5 plus 5. So that's going to give us a positive 1.4 kilonewtons. Finally, the shear force between D and A. So we go to shear force between D and A, which is going to be this 1.4 kilonewtons minus the 2 kilonewtons at D. 2 kilonewtons at D, and that's going to give us negative 0.6 kilonewtons. So those are the values of the shear forces, and we are going to use these values to plot a shear force diagram. Now, this is what we are going to have. We are going to have that line of origin, the line of origin. We begin with the shear force between C and E, which is 0.4 kilonewtons positive. So approximately that point, like that. So that is 0.4 kilonewtons. Then the shear force between E and B, negative 3.6. So it is going to appear below this line because it is negative. Positive shear forces will appear above this line of origin. Negative shear forces will appear below this line. Therefore, 3.6 kilonewtons, let's approximate it to be at that point. So we are going to have a shear force of 3.6 kilonewtons, which is negative shear force. This one is a positive shear force. The shear force between B and D, 1.4 kilonewtons. So 1.4, let's approximate it to be at that point. So we are going to join with a straight line, and we drop to the line of origin. So this is a positive shear force, a shear force of 1.4 kilonewtons. Finally, we have the shear force between D and A, which is negative 0.6 kilonewtons. It is going to appear below this line. So negative 0.6, approximately that point. So we are going to have it like that. So that is a negative shear force of 0.6 kilonewtons. Therefore, ladies and gentlemen, engineers, structural engineers, civil engineers, that is how we usually plot a shear force diagram for a continuous beam. So just to remind you, my dear friends, if you are yet to subscribe to our channel, please consider doing so. Let's grow this channel and make it move to the next level. Make it move to the next level. Very good. So down here we can write S.F.D, denoting shear force diagram. Therefore, thank you very much for watching our video, and please, as we have said, as we have requested, don't forget to subscribe. Thank you very much.